Hi everyone, and welcome back to the last lecture video in the quantitative data analysis lecture. In the previous lecture videos, we've explored univariate statistics and visualization techniques. But now I want to focus on these analyses that include multiple variables. Now there are numerous types of multivariate analyses. They can be simple bivariate analyses that only look at the relationship between an independent variable and a dependent variable. Or they can be complex calculations that involve dozens of different variables all at the same time. Most of the multivariate statistics that are published in research are way beyond the scope of this course. But I do want to teach you some basic data visualization techniques that you can use to make preliminary analyses about your independent and dependent variable relationship. One of the most important things that you'll need to know then for this analysis is how to create a bivariate table. This type of table allows you to examine the distribution of subjects across the independent and the dependent variables at the same time. Here's an example of a bivariate table showing the relationship between victims and their offenders and the victim's sex. The tables contain a lot of good information, so it's important for you to be able to break down what a bivariate table actually consists of. One of the first things that bivariate tables can tell us is the type of variables we're dealing with. Now, each discipline has its own standards, but in social science, the independent variable attributes will each get their own column, and the dependent variable attributes will each get their own row. So just by looking at the table itself, you can identify the independent and the dependent variables. For instance, on our example graph, we have two different variables, victim gender and victim offender relationship. Since the attributes of victim gender have their own columns, then that's going to be my independent variable. Since the attributes of the victim offender relationship have their own rows, there's my dependent variable. So I know now that the author is trying to explain how the gender of a homicide victim impacts the relationship between the victim's attacker and the victim themselves. Something that people don't always realize is that contained within a bivariate table is actually two standard frequency tables, one for each variable. These tables are found in the last row for the independent variable or the last column for the dependent variable. We call these marginal totals. Marginal totals show the sum of an entire column or row. They themselves can then show us the breakdown of each variable by itself in the sample. In this example, we add up all of the male victims, 496 that were killed by intimate partners, 1,309 killed by family members, 6,273 killed by acquaintances, and 3,334 killed by strangers. That gives us the marginal total of 11,412, which means that in our sample, there were 11,412 male victims overall. We do the same for the female victims and find that the sample contained 3,335 female victims, which gives our sample a total size of 14,747. The marginal total for the dependent variable works the same way, except now we're adding up all the values within a single row to get a total number of victims within that are killed only by an intimate partner, that are killed only by a family member, so on and so forth. So even within a bivariate table, we can analyze the distribution of each variable by itself. Now, bivariate tables have the same issues as regular frequency tables. If there are unequal totals in the rows or columns, then we cannot compare directly without standardizing the values first. For example, in this chart, there's an unequal number of male victims and female victims. So we cannot directly compare the frequencies that were provided in the original table. So how do we know if victim gender is actually influencing the victim-offender relationship or not? Well, first, we standardize the values. There are several different types of standardization statistics that are used in bivariate tables, but the most important one for social science, and for this course, is the column percentage. The column percentage can help me figure out whether or not there has been an impact of the independent variable on the dependent variable. The column percentage formula looks very similar to the regular percentage formula, but this time the capital N refers to the column total only, not the total sample size. This allows us to calculate the percentage of each value in relation to the total cases within that column only. You can see this column percentage here in the male victim intimate relationship cell. I have created a column percentage by taking the frequency value from that column in the 400s, dividing by the total number of that column, which is 11,000, and then multiplying by 100. This tells me that 4.35% of male victims were killed by an intimate partner. Notice the of male victims refers to the of whatever the total N was that you were using. So 4.35% of male victims, because my N that I was dividing by is the total number of male victims. Now I do the same thing for female victims, and I find that 44.17% of females killed were killed by someone who was in an intimate relationship with them. So now this type of percentage is going to allow us to compare both columns. You can see the benefit of standardized values clearly with these two completed tables. On the table on the left, unstandardized values show us the specific values in each cell or in each column or row, but they don't allow for any meaningful comparisons. The column on the right, or the graph on the right, uses standardized column percentage values, which now allow for an easy comparison. By the way, quick tip, you can always figure out what type of percentage you're using by looking at where the 100% are. If you are using column percentages, there will be an 100% at the bottom of every column. The other type of percentages, row and total, will have 100s at either the end of the rows or only in one cell on the table. So look out for the 100% all the way across the bottom of the table. That'll tell you whether or not you're dealing with column percentages. Just like univariate tables, often we find that bivariate analyses are better depicted with charts and graphs. Multivariate bar graphs are one way that we can show distributions of multiple variables in the same graph. The bar graph on the left is called a stacked bar graph. It's basically like 3 pie charts stuck together vertically, one for each category. While this can be helpful with major differences or to illustrate a pattern, this type of bar graph is not very good for displaying actual values. For instance, trying to figure out the specific value of that orange bar is really hard because it starts somewhere in the middle of the chart and it ends somewhere else in the middle of the chart. But you can easily see that the percentage of red values, indicating freshmen, is decreasing each year, and the percentage of the yellow values, which indicates juniors, is increasing. So an overall pattern. Now, clustered bar graphs are much more common. These graphs look like 3 separate bar graphs merged together, with colors or patterns used to distinguish between the different variables. In this example here, the graph is designed to show us the distribution of freshmen, sophomores, and juniors by each year. So time is the independent variable, as we are wondering what kind of effect time is having on student class, the dependent variable. Like clustered bar graphs, line graphs can also be used to depict the distributions of multiple variables at the same time, using either the color of the line or a pattern in the line to distinguish between 2 different variables. One caution here is to avoid clustering too many variables into the same graph. Notice how 4 lines on the graph to the right, only 4 lines are really visible. Everything else is just kind of a cluster at the bottom, right? In this case, breaking the graph into multiple graphs would be the most helpful so as to better illustrate the breakdown for all of the categories that are shown. Now, one caveat that I do want to say is it's not always the best thing to provide the readers with a complicated multivariate graph. Sometimes a simple univariate graph repeated for each category of the independent variable can actually illustrate the point best. Again, remember my theme with graphs: simplify, simplify, simplify. All you care about is how the graphs convey the information, not how fancy they look. Now, your textbook covers several more types of multivariate analyses, and I'm not going to cover these in depth because they're way more advanced and I don't expect you to be familiar with the calculations for them in this course. However, I have highlighted one of the analyses here on this slide, and that's regression analysis. This type of analysis is really popular in explanatory research because the goal of a regression analysis is to predict values of the dependent variable based on input about the independent variable and control variables of interest. So you can imagine that this type of prediction is super intriguing for criminologists. We could use this to predict public attitudes, criminal activity, etc. All right, almost done. The last thing I want to leave you with is this idea of statistical significance. Statistical significance is the key goal for published research. But this is solely the statistical association that we talked about as a requirement for causation. Remember that I said statistical association is one of the easiest things to create. Given enough data and enough analysis manipulation, we can make almost anything statistically significant. So as a critical consumer, I want you to keep in mind the difference between statistical significance and practical significance, or substantive significance, as your textbook calls it. Just because something is statistically significant doesn't mean it should be taken as important. Imagine, for example, if we were running an experiment on a new weight loss program. We have two groups, one doing this program and one not doing anything at all. After 3 months, we find a statistically significant difference in the weight between the two groups. But the actual weight difference is only half a pound. So the new weight loss program caused participants to lose half a pound more than those participants that didn't participate in the weight loss program at all. Is this half a pound statistically significant? Yes. Is it practically significant? Not likely. So it's important to be aware that the term statistically significant may not always be as important as it sounds. Woohoo! You made it! That completes our discussion about quantitative data analysis. Thanks for watching, everyone.